Okay,
It's like one
let's keep going. So we have conservation before and conservation after. So we still have to figure out this part here. So P1 prime is equal to M1 times 7.5, and P2 prime is going to be equal to 65 times 118 meters per second. Now, we have the satellite going in one direction, and we have the thrusters going in another direction. Okay? So we have the satellite arbitrarily going to the left, and we have the thrusters arbitrarily going to the right. We can set that up this way, because that's how it's going. However, I would put the negative sign on the thrusters because I have the unknown in the mass of the satellite. And it's arbitrary. We're not told which way they're going. We get to pick the direction. So that's what I would have done. But because I drew the picture this way, and to keep things straight in our heads because we're learning a new concept, I'm going to put the negative sign on the satellite. Okay? It'll still work out in the end. So here we have 0.7 negative, 0.75 M1 plus whatever 65 times 118 is.
Why is it 0.75?
It's not. It should be 7.5.
Okay.
Good catch.
Thought I was.
7.5. But did you have a value for that, Sophia? Is that what you were saying?
Oh no, I said
Oh,
Is it
'cause I-
70?
had a dull moment in my thinking.
It's like,
Yes, sir.
is it 7,670 for the right side?
Yes.
Okay. Then you bring that over and you divide it by negative. Odd.
Yeah, so then Jaden's got it figured out.
Negative 10,022.
So here we have before, we got to bring over everything. So we have 0 minus 7670 is equal to negative 7.5 mass 1. Because we're isolating, we put all of our knowns on one side and we leave our what we're looking for on the other side. So we have negative 7670 divided by negative 7.5 is going to be the mass of our satellite. And we get what?
1.0 times 10 to the 3 for 1,022.6.
Okay, so the mass of the satellite is 1,000 kilograms, which I believe is a ton.
Is what?
A ton.
Yeah.
I'm not 100% sure.
Me neither.
There's tons and tones, and I don't know them very well. Okay, everybody has this written down. Cameron's like, I'm just gonna pretend I'm following along. How was volleyball, Cameron? Good. A 1.1 times 10 to the 3 kilogram car traveling east at a velocity of 25 kilometers per hour collides. So this is a collision. Head on with the second car traveling west at a velocity of 15 kilometers per hour. During the collision, the two cars lock together. If the velocity of the locked cars is 3.3 kilograms per hour east, what is the mass of the second car? One of the things that we don't have to do in this question because it's consistent all the way across is we don't have to change the velocity. Just like in the very first question, we didn't have to change the mass because the mass isn't what we were looking for. Neither was the momentum. We were looking for the velocity. So as long as your units stay the same throughout the whole question, if it's not what we're looking for or momentum is not what we're looking for, we can leave it in kilometers per hour. One less calculation for you to make a calculation error on, right? Okay, just so you know. So what does our image before look like? Exactly. We have a car traveling east, and we have a second car traveling west. What does the image look like after? They're locked together. And then what else do we know? Just in drawing the diagram, what else can we put in there?
Correct.
And which way are they going?
One's going east, one's going west,
Before?
and then afterwards they're locked and they're heading east
They're headed east.
at 3.3 kilometers per hour.
Perfect. So then now we can write in our unknowns. So here we have so over here, because they're locked together, what do we know about the mass? Because they're locked together, what do we know about the mass?
It's all together.
All together.
So we only have one mass throughout this entire equation.
So the total mass over here is 1.1 times 10 to the 3 plus mass 2. Okay, what do we know about velocity over here?
The entire thing is going 3.3 kilometers per hour.
Okay, and one more thing that we have to pay attention to.
The units are in kilometers per hour.
Yeah, but that's what I was just saying, that because we're looking for the mass and all of these units are the same unit, we're not looking for momentum, which relies on us going back to kilograms meters per second. We can leave that like that because we're just looking for mass. But there is one more important thing than that. It will trip you up, mess you up, and it's a common error.
R2 is negative.
Card 2 is negative. Why is it negative?
It's headed west.
Because it's headed west. Okay? Make sure that you're including that. It's negative. 15 kilometers per hour. So, the sum of the momentum before is equal to the sum of the momentum after, or we could say, quite often you'll see this. You'll see P prime. P and P prime means the same thing. So we have car 1's momentum. And we have momentum of car 2. Over here, we have the total momentum of the cars together is equal to m2 plus 1.1 times 10 to the 3 times by 3.3 kilometers, oops, Okay? So 1.1 times 10 to the 3 times 25 kilometers per hour is what? Everybody's looking at you, Sophia. This one here? Say it again.
That's a big car.
And then the second momentum is 15 times m2. Negative. Let's not get the negative sign. Over here, we have and then what's 3.3 times 1.1 times 10 to the 3?
$3,630.
M2 okay. So when we isolate this, we're going to have 27,500 minus 3630 is going to be equal to 15m2 because I'm bringing this over. So what do we have for this value here? Yeah. So, sorry, say it again. 23,870. And this over here is going to be 18.3 M2. So M2 is going to be equal to 23870 divided by 18.3. Okay, what do we get?
Correct.
Okay. So you can see why making sure putting the signs is important. Okay. All right. I'm going to let you have whatever's left of class time to work on your labs. It's up on Google Classroom. Dump it in there. I'll be notified when you're done. But this will be the only class time that I give it to you. Okay?